Hello, Fusion fans. Dr. Matt Moynihan here. I wanted to do a deep dive on inertial fusion energy. And I want to start by saying that I'm a little bit of a skeptic of this approach. I did a PhD in this in 2006 to 2013, and I got an up-close and personal view of all the struggles that researchers go through to make these systems work. And I left my PhD wondering, how the heck are we going to turn this into a power plant? So I went off and did a whole bunch of stuff, and now it's about 10 years later, and I'm coming back and I'm looking at a field that's very different and has a lot of exciting aspects to it. There's been a lot of developments that get me excited. In addition, there's a lot more money running around chasing these fusion concepts. And if you had unlimited funding, I think there's a set of technologies here that could be cobbled together into a power plant. So let's get excited. So to start, this field breaks into two subcategories, drivers and targets. I'm going to talk about drivers first. The field has long looked at a variety of drivers. The first one is a projectile solid object. You can fire an object at a target, and the idea is that you can get fusion with that. Now, that's been demonstrated by first light fusion. The velocities that people were kicking around were somewhere on the order of 1,000 meters per second, or 1,500 meters per second, or 2,000 meters per second. I'm skeptical that the projectile approach can work at a large scale. So I'm going to set that aside for the moment and look at the other driver. The other driver was beams of particles, both ions, electrons, and heavy ions. This has been studied. It was studied for 15 years in the 1970s, the 1980s at Sandia National Laboratory. And there are a lot of problems with this. So one thing, if you throw a bunch of electrons at a target, they tend to just go everywhere. They kind of just, wander around everywhere, and they don't focus on the target. You can get some compression, but it's not great. So people switch to light ions, and then eventually they switch to heavy ions because they have more mass. And today there are still a community of people that are pushing heavy ion fusion using these beams. And the advantage that they point to is that the particle accelerators can be very, very compact. So they're very small, and they can get particles up to the right speed. Now, I'm skeptical of this because even if we got the particle beams to work as well as the laser system works, we're still going to run into many of the problems that NIF sees with diluting the compression and screwing up how you get energy on target. So the particle beam systems, I'm going to also set them aside. So what's left is lasers. So, of course, lasers have the most funding and research behind them. So I want to look at them first. Now, I said earlier I was a skeptic because I did my PhD on the Omega laser system. And the problem, the first problem is one of repetition. How do you shoot over and over and over and over again with no maintenance issues, no problems, and maintain a power plant? I didn't see how to do that when I left my doctorate. Well, now it's 2022, and I've actually seen an ICF system that can go bang, 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 bang. In fact, I'm going to play a clip of it. Incredible. This work was done at the Naval Research Laboratory using the Nike and Electra lasers. And what's different about them is that they are gas-based laser systems. That is what's fundamentally enabling high repetition shots there. So that's the big divide in laser drivers between gas-based systems and solid-state systems. Omega, NIF, the laser megajoule facility in France, the Eli beam in the Czech Republic are all solid state system lasers. They use big blocks of glass to make their laser beam, and then they send that laser beam through hundreds, if not thousands, of optical elements, including lenses, mirrors, gratings, frequency conversion sets, or for chirp pulse amplification through vacuum systems. So solid-state lasers, blocks of glass, heat up. They have a high heat capacity, so they can heat up, and that's their first fundamental barrier to shooting many times in a row. You have to wait for the glass and the optical elements to cool down. So on Omega, that was about 45 minutes. And typically the Omega system would only shoot 2, 3, 4 times a day. Now, Nike can shoot every 2.5 hertz, so, many, many times a minute. And the reason why is because the gas does not get hot. The gas has a low heat capacity, and you can ignite it using arcs of electricity. So the NRL has developed an approach that's much more exciting and lends itself much better to a power plant. Now, the disadvantages are that no one's ever built a large NIF scale facility using gas-based lasers, and it's unclear how you would do it because you don't have the optical elements. They haven't been designed or built at the scale you need with that laser light that specific laser light. The other difference in solid state versus gas-based systems is the smoothing techniques. Solid state lasers can and are smoothed. The beam of light that comes out of the laser system can be shaped, smoothed, reshaped, and you can distribute energy up front of the pulse and in the back of the pulse. Omega does this really, really, really well. Solid state systems emerge from the gas less distorted because they're not traveling through the solid. So they don't need as much smoothing, but also the techniques for smoothing a solid state gas laser are not as well developed. So there's a smoothing difference between solid and gas-based systems that has to be accounted for. So let's go back to those optical elements. They heat up, and that's a problem. So the people that want to build a power plant out of a solid-state laser have proposed various ideas for how to get around this heating up problem. One idea that they'll throw out is actively cooled lenses. So you have lenses with water around the outside that pulls heat off the lens. Now, on the face of it, I don't like this idea. I don't think the system should work against itself. You're putting the machine against itself. You're fighting yourself. Another option is to remove as much glass as possible. This is, of course, more interesting. People have proposed ways of pulling the glass out of everywhere they can, out of the final optics, out of the beam line, out of the pulse train, out of the amplification. Just anywhere you can remove the glass is always a good thing. And I've seen some proposals that remove a lot of glass through a different laser architecture. So that's another really good idea. Third idea, is to keep the beam diffuse and not focused. So if the light is passing through an optic over a large surface area, the amount of energy imparted is lower than if it's focused. So that's one way. You want to keep the beam as diffuse as possible, as long as possible, and then focus at the very end. Now, a fourth idea is plasma optics. This is a really interesting area, but it's a low TRL, so very low maturity technology when compared to solid glass lenses. This concept has been around since the 1970s. The idea is that you have a laser pass through a plasma with maybe another laser or some sort of condition in the plasma, and the laser will emerge with some effect taking place, either an amplification or a compression or a reflection. This got a lot of money in the 1980s because of the Star Wars program under Ronald Reagan. They were trying to project laser beams into space to shoot down missiles. And so they had to develop all these techniques and demonstrate them at scale. And so today, a lot of fusion companies that are looking at plasma optics are pointing to that work from the 1980s and say, hey, this has already been demonstrated. Let's now implement this into a power plant, and we'll have these wonderful techniques for getting to very high powerful lasers and doing things that won't heat up because there is no glass in the optics. The basic element of a plasma optic is a chamber with plasma in it. And the plasma inside has to be controlled in a large enough scale to deal with the laser energy. So the laser beam will come in, it will interact with the plasma, it will interact with maybe another beam that's coming in, and you will get that effect. And that means that there has to be a chamber itself around the outside, which means that there is some physical glass. You can either have windows on either side of the chamber with the laser passing through it, or you can have a shutter situation where you form the plasma, have a shutter, the shutter opens, the shutter closes, it remains closed, the beam comes in, it interacts, then it opens, and the light passes out the back side. But then the plasma would need to be refreshed. This is all very, very challenging work to do. Now, plasma optics lend themselves well to the excimer gas-based laser system. On the solid-state side, the supporters of that approach are pushing for better laser diodes. Now, what is a laser diode? The function of a laser diode is to convert electrical energy into light. And you're trying to do the most efficient method for doing that. And circa 2015, the Happel's system that was delivered to the Czech Republic is sort of the baseline. And that was anywhere from 45 to 50% efficient in turning electrical energy into laser light. The function for doing that is called the laser diode bar. It's a block of material that acts like a semiconductor. And so at the time, the limit was about 500 watts per bar. Today, that's about 2,000. Pioneering breakthrough research in Germany has basically enabled them to go to 2,000 watts per bar, but that's not commercially available. So the solid state people are saying, hey, let's make these more efficient laser diodes, and we'll be able to get more bang for our buck, and that will also lower the overall cost, because at one point it was estimated that the laser diodes were, more than 50% of the cost of the entire laser system. Because the optics are supposedly cheap. So that's all included in the forthcoming national report issued by the Department of Energy Basic Research Needs Study. They're calling for these laser diode development. Okay, so let's change gears and look at the targets. This is an open area of research, and it's also an area where there is no consensus. Because compression on the ICF hardware is so complicated, it happens very quickly. It has a lot of related processes. It's hard to model. It's hard to measure. It's hard to observe. There isn't a general consensus about the best way to compress a target. You would think there might be after so many years and decades of research, but in fact, there are different schools of thought on how to do this because compression is really complicated. A case in point, ignition was really hard to do, and really hard to do repeatedly. At one point, the National Ignition Facility was struggling to get repeatability in their experiments. They were basically putting in the same inputs and getting different outputs, which breaks a basic law of scientific experiments. You want to do the same thing over and over again and get repeatability. That's how you prove an effect. Well, the ignition facility was struggling to get repeatability because ignition compression is so complicated. That was the problem. So what has evolved are these different schools of thought about the best way to do this. So I'm going to go over, everyone agrees that the best approach is a low adiabatic approach. Now, what does that mean? That means that when a plasma gets hot, it is hard to compress because it's hot. So what you want to do is you want to compress first while it's cold and then heat it up after the fact. Compress first, keep it cold, then heat it. So there are 3 approaches, direct drive approaches, that do this. Now, there is a difference between direct drive and indirect drive. Direct drive is where the lasers go right on the target and compress it. Indirect drive is where the lasers hit a gold foil around the outside, and they are converted into X-rays. When the laser hits the gold, it's converted into X-rays, and these X-rays bathe the target and compress it. Now, why would anybody want to do that? Well, the reason you want to do that is because of weapons. Basically, it's a weapons-driven experiment. It's a National Nuclear Security Administration driven experiment, and that's what NIF does, is a weapons driven line of research. And so if we're not interested in weapons and we're interested in fighting climate change and solving the energy crisis with fusion, we want to look at the direct drive approaches. So let's look at 3 direct drive approaches. The first one is central hotspot ignition. This is kind of your traditional, conventional, vanilla, run-of-the-mill type compression. Basically, the target is compressed and it forms a hot spot in the center that's maybe 10 million degrees Kelvin or higher around a relatively lower density plasma around the outside. Inside that hot spot, the idea is you get ignition, you get fusion reactions that then chain together and cause other fusion reactions. This was hard to do. So in the early mid-2000s, researchers came up with the idea of a shock ignition. Basically, you lead with a low energy pulse that causes the compression to happen, and then you close with a high energy shock wave at the very end that shocks the target to close. And about 300 megabars was typical for that. So shock ignition, very exciting. A third approach is fast ignition. This is a combination of 2 lasers, a conventional laser that compresses the target, and then a second laser pulse or beam of particles that comes in and heats it once it's compressed. The analogy often used for this is a spark plug. Or a piston on a spark plug. You compress the engine piston and then fire, and then it explodes off. And so that's what fast ignition is. Now, Focused Energy has called for doing an entire power plant using fast ignition. And one of the caveats of that approach is that you have to have these gold cone attachments to your targets to do that. And that's challenging to mass produce. I don't know how you're going to mass produce 10 million gold cones a year and glue them onto the target. Not clear to me how you do that. Those are 3 different schools of thought, and there are other ones. There's a thing called stud pulses, where you basically randomize the amount of energy in the pulse to try to get compression. There's this idea called star driver, where you have 10,000, 100, or 100,000 small, cheap, low-energy laser beams shining on one target that give you basically infinite flexibility in terms of bandwidth, color, pulse shaping, and all sorts of other things to try to get the best compression. And then there's this, but Excimer Energy Company is proposing to take a really big target and compress it with 2 laser beams from 2 different directions. So the bottom line is there's no consensus about this. There's no consensus in the ICF community about the best way to compress a target because it's so complicated. And it may turn out that multiple approaches work simultaneously. I don't know. So let's talk about targets for a minute. How do you mass produce these targets? Now, what is a target? The basic building block of a target is a foam shell, or a foam or polymer polyamide shell, or glass shell that contains deuterium and tritium. And a whole lot of things have been tested as targets: blocks of material, cones, small pellets, things with weird configurations, stuff with magnetic fields attached to them. Lots and lots of things have been shot as targets for various reasons to do experiments that aren't related to fusion at all. But for a fusion target, the basic building block is a pellet with fusion fuel inside it. That is the basic building block. Now, you can overcoat it. You can have layers of material over the top, including plastics or gold or some other metal. People have looked at adding carbon nanotubes around the top. That has been looked at. Blocks of solid material have been looked at. There's also, first light fusion is going to have an amplifier block around the outside that causes the compression wave to come in from one side and then compress around the target. Very interesting idea there. The focused energy, like I mentioned, has the solid pellet with this gold cone attached to the outside that it funnels in the second laser shot. So there's that. And then there's, of course, the size. So the pellet can be small. A small target might be several hundred microns in size. Larger targets might be 2 or 3 millimeters. I've seen some targets that are 5 and 7 millimeters in diameter. Those are big mega targets, basically. Of course, the bigger the target, the more fusion fuel it has. And so, therefore, the larger the gain you would ostensibly get from getting that target to ignite. So bigger targets are advantageous for a lot of things. And I think if we do this for a power plant, it may be that we go to these really big, fat targets that have lots and lots of fuel in them. So we get more bang for each shot that we do. I also want to point out that mass dilution is an issue. Anything that is not fusion fuel in a target will be disruptive. Any extra plastic you add, any extra metal you add, if you add glass or carbon or something else to the fuel mix, you're going to dilute plasma at the end of the day. You're going to dilute the plasma, and that's bad. You want to avoid that. So how do you make a foam shell? General Atomics generally makes these foam shells. They start out as droplets in droplets, double emulsions, oil in water in oil droplets that are made using something called a triple nozzle generator. It's a pipe with a glass around the outside, and water and oil and water are flowed through this, and they form up into these double droplets inside droplets. Now, the water layer contains some chemicals that can be used to foam up and solidify into a foam shell. The General Atomics makes these double emulsions. They send them down into basically a big vat or tub. They continuously stir that tub, and Brownian natural motion kind of centers it. It's not a very good method for centering. There are other approaches to centering that are more in a low TRL researchy stage, but once they're centered, they're heated or zapped with UV light so that they're cured or solidified into a foam pellet. They've looked at plastics for this. They've looked at solid shells for this, like glass shells, variety of different materials to make these pellets. The pellets are then washed in a set of solvents and then critically point dried, which is probably the best way to make sure that there's absolutely no fluid left in there, even though they start their life as a droplet in bathed in fluid. The goal is to get them completely dry. So the critical point drying does that by putting them in a vacuum chamber and slowly ramping up the pressure so that it dries out all the stuff in there. Now, once completed, those foam shells are then shipped to the laser facility where they're brought in, they're inspected for quality. If one is selected, it's mounted in some way on a stalk or a cold finger or with a fill tube or something, and then placed inside a vacuum chamber. Now, inside the vacuum chamber, you can do things like coat it, for example, and there's various ways to do that. Or you can start immediately characterizing it and cooling it down to cryogenic temperatures. Let's say you just do that. So you cool it down to cryogenic temperatures with deuterium tritium gas on the outside. Now, the gas condenses into a fluid, and that fluid eventually freezes into the shell. So what's happening is the DT is finding its way into the foam and forming a liquid in there and then freezing into an ice structure. The ice is embedded in the foam shell. The two are inseparable, basically, and the gas is inside that. That's a cryogenic deuterium tritium target. Now, there is a whole set of people that say you don't need to go to cryogenic temperatures. You can do it with just gas, deuterium tritium gas in the center. So there's that option as well. Once formed, that cryogenic target has to be brought to the laser facility center. The way this is done at the LLE is they have a cart that's the size of a Zamboni. Basically, you can think of a giant Zamboni on wheels that has the chamber inside it with the cold target at the end of a cryogenic cold finger. The cart is then pushed into the laser facility. An elevator elevates it up. It's then extended up into the target chamber. The last second, the shroud is dropped. The cryogenic target is exposed to normal air, and it starts immediately becoming gas. But right then, the laser comes in and compresses it, and you get nuclear fusion. Very complicated, very difficult process to do. It's a very complicated, very hard process. There are proposals for how to improve the quality of the target. There are, of course, easier ways to mass manufacture that first part, the foam shell. Not filling with cryogenic fuel is one way to, get around a lot of problems. You could put the deuterium tritium directly in as gas, but you have to permeate fill. And it takes a long time to do that, but there may be ways to do that where you could pressurize up. That's been looked at, I should say. But anyway, filling the target is a problem. Making the foam shell is a problem. For all these reasons, I think going to larger foam shells will probably be needed, especially if you want to avoid cryogenic temperatures. You want to just do gas. You won't have the fuel as dense as you'd like it if it's doing a gas system, so it's going to be a larger foam shell. Anyway, that's all I have for targets. So IFE is an exciting place right now. There's a lot of money looking after this, and there's been about 6 or 7 companies that have formed around doing this as a power plant. Now, they are way behind the magnetic confinement folks. I think way behind. Tri-Alpha Energy already has a fully formed company with a complete machine that already does experiments on the regular. General Fusion, the same thing. And as an investor, you want to look for potential spinouts. If you were going to put money into the IFE approaches, what are the spinouts? The laser systems have some spinouts with directed energy weapons. I don't even know what would be applicable if you had such a powerful laser, maybe using gas-based systems with plasma optics. I'm not sure what could be applicable there. Mass producing small foam shell targets, very challenging problem. You can 3D print them, but it takes too long, and the characteristic size is not great. The better solution is microfluidics. There's a lot of stuff that's already happening with microfluidics, so it's not like you would dovetail that technology. People are doing microfluidics are already using it for all sorts of medical applications, so I don't know if there's great technology spinoffs there. But in general, if we're looking for fusion energy, IFE has a lot of people already invested in it. It doesn't get enough support from the federal government, and it should be looked at more extensively by private investors. For instance, I'll just give it for instance. Congress created this inertial fusion energy program 2020, and they called for 25, they got 5, and then I think 3 million was actually handed out, or this year, excuse me. The thinking, by the way, with that was the federal government already spent billions of dollars on weapons programs. And what if we give a little bit of money to this IFE thing? And what will happen is that little bit of money will basically piggyback off all this existing funding that inertial fusion energy has received over the years. I don't know in practice how well that works. I think there's a lot of lab directors that are more skeptical of that. So I don't know how well that works. Anyway, it's an exciting time. Thanks for your time.